ever wonder if there are any volcanoes in the Bay Area? Well, that's a valid question given that we're at a major tectonic boundary. Here I am at Sibley Volcanic Preserve off Skyline Boulevard in Oakland. And you wonder why it's called a volcanic preserve? Well, here in the park is the remnant of a 10 million year old extinct volcano. And at first glance, this might just be a beautiful place to go for a mountain bike ride, take your dog for a walk, or go for a run, which it is. But upon closer inspection, it is a super interesting place geologically. It is the remnants of an extinct volcano that was active about 10 million years ago. And I bet you had no idea we had a volcano in our backyard. Might be a little surprising that we have evidence of volcanism here in the Bay Area. We are at a transformed plate boundary, which is the boundary between the North American plate and the Pacific plate. And that type of boundary is normally associated, yes, with earthquakes, but not so much with volcanoes. So when you look at this area, it might not look like a typical volcano, like the Hawaiian volcanoes or any of the Cascade volcanoes. It does not have that classic shape of a stratovolcano. And that's because this volcano has been distorted, sheared, moved around, and actually is now on its side. So it does not have that classic volcanic edifice. But it has a lot of volcanic features that give clues that it was a volcano 10 million years ago. There are ash layers, there's basalt. And you might be wondering, what kind of volcano was it? Was it highly eruptive? Was it explosive or more effusive? And if we learn a little bit more about volcanoes, we might be able to extract some clues as to what kind of volcanism occurred here between 10 and 9 million years ago. So let's go ahead and start learning about volcanoes, and maybe we can piece together some clues about this area. There's a great range in the explosivity of volcanic eruptions. Many eruptions are relatively quiescent, and the lava seems to be oozing out of the volcano or fissures on the volcano over the surface of the earth. Other eruptions, however, are highly explosive, and they're characterized by violently ejected volcanic debris. And this can extend tens of kilometers into the atmosphere above the volcano, and you don't want to be anywhere near these type of volcanic eruptions. Whether an eruption falls into one of these end members depends on a variety of factors. And these factors are ultimately linked to the composition of the magma, of the molten rock that is underlying the volcano. So let's look at some of the features of the magma that would determine whether a volcano erupts kind of quietly or violently. The reason the composition of the magma is so important is that it determines in large part the magma's consistency or its thickness. And geologists don't use that word, they use the word viscosity. And in a more exact sense, the word viscosity can be defined as the ability of a substance to resist flow. So you can think of viscosity, which is the opposite of fluidity. A material that has low viscosity are very fluid and very mobile. So you might think of something like water. High viscosity fluids are very thick and very sticky, so you might think of honey. And viscosity of lava is really important because it affects how it behaves and is directly related to the violence of a volcanic eruption. So what are the parameters that would make a lava more viscous and therefore have a more violent explosion, or less viscous and have a more quiescent or oozing eruption? And viscosity is important because it determines how easily gases can escape from a volcano, and that will have an effect on how explosive the volcanic eruption is. About 1 to 5% of all magma is dissolved gas, water, carbon dioxide, among other gases, and the escaping gases are really what make volcanoes explode. It's not that the magma is pushing out hydraulically, it's that the gases are expanding and trying to get out of the magma. The low viscosity magmas, ones that are very runny, can flow easily over the Earth's surface and may form lava rivers and fountains. Magmas that are highly viscous, meaning they're very thick, they don't flow very easily and usually form crumbly rock lava flows that look like piles of rock that are moving downhill. So they behave very differently on the surface of the Earth, in addition to creating a different type of volcanic explosion. So what affects the viscosity of the magma? There's three main pieces of it. One is the temperature. The second is the magma composition, and we're referring mostly to silica, and then also the degree of crystallization. So let's review those three and how they affect the viscosity of a magma. So temperature's influence on viscosity is intuitive. You know, for example, if you have syrup and you want to put warm syrup on your warm pancake and you heat it up, what happens to the viscosity of that syrup? Its viscosity lowers as the temperature increases. The same can be said for magma. The higher the temperature, the more fluid it becomes. And on the other hand, the cooler magma is, the thicker or more viscous it is. When we talk about the temperature of the magma, we're talking about the temperature of the magma before it erupts. But it's clear once the magma reaches the Earth's surface and erupts and becomes lava, the temperature will start to cool down. And the nature of that lava will change as it cools down. As it erupts, if it's very fluid, it will then start to cool due to the temperature of the atmosphere, and it causes a surface skim to form over the lava. Although underneath it's still hot and is flowing, it will have kind of a surface to it. And that's called a pohoi flow. So initially the surface skin is smooth and this kind of ropey texture. And these pohoi flows tend to be thin, and because of their low viscosity, they can travel long distances from the vent. But then as this lava cools down, it becomes more viscous and will form kind of rough, jagged blocks that push forward. And this type of lava flow is called aa. And it's kind of a rough, clinkery surface indicating it's flowing at a lower temperature at that point. And there is a transition from this pohoi flow to the aa flow as you get further from the vent and the magma and the lava starts to cool down. Let's dive a little bit deeper into why the amount of silica in a magma chamber would have anything to do with the thickness or the viscosity of the magma. Well, a small silicon atom often gets surrounded by 4 larger oxygen atoms, and this atomic configuration of SiO4 is in the shape of a tetrahedron. The silica oxygen tetrahedra can be linked together to form a variety of shapes. And one of the common ways that they attach is by forming a long kind of infinite chain of these tetrahedron, and almost like strands of hair. And this makes the lava really kind of clingy and sticky and much more viscous, which would then trap gas, making a more violent explosion. Magmas that have a high silica content will therefore exhibit a greater degree of polymerization and have higher viscosities than those with low silica content. Third factor that would affect the viscosity of a magma is the degree of crystallization. If the magma chamber is very warm, there would not be any crystals that have formed, but as the magma starts to cool down, certain minerals will crystallize out first, and they will serve to make that magma thicker because they are solid crystals. So magmas that are 100% melt or 100% molten would have a lower viscosity than one that has crystals that have already formed, making it thicker. So it will become a crystal mush if crystals have formed, and that would increase the viscosity of the magma. So why do we keep saying that a more viscous magma creates a more violent explosion? Well, it doesn't necessarily have to do with just the viscosity, it has to do with gases. Most magmas have between 1 and 5% gas content. It contains water vapor, carbon dioxide, hydrogen sulfide, sulfur dioxide. At depth, most of the gases are dissolved into the magma. And it's really this gas, as it's reaching the surface of the Earth, that provides the driving force for explosive eruptions. So magma that are generated deep within the Earth, they begin to rise because they are less dense than the surrounding solid rock. As the magma rises, at some point they encounter a depth or a pressure where the dissolved gases can no longer be held in solution in the magma, and the gas begins to form a separate phase. It makes bubbles, just like in the case of carbonated beverage. When the pressure is reduced, the gases want to escape. So what happens to these gases as they near the surface of the Earth? Well, that really depends on the type of magma that the gases are in, and that once again depends on the viscosity of the magma. So let's take 2 scenarios involving one with low viscosity magma and one involving higher viscosity magma. A low viscosity magma, like basaltic magma that's very runny, will allow the escaping gases to migrate rapidly through the magma and escape to the surface. The gas bubbles will form. It'll continue to grow in size as the pressure is reduced, and more of the gases will come out of solution. So the gases can expand and reach the surface. If the liquid part of the magma has a low viscosity, then the gases will escape easily, and it will produce a effusive or non-violent eruption, such as a lava flow. On the other hand, if the liquid part of the magma has a high viscosity, the gases will not be able to expand nor migrate to the surface. Since the bubbles will be prevented from rapid escape, the bubbles will be held in the magma, and the overall pressure will increase until the magma chamber erupts explosively in the form of a volcano, and it will produce a whole lot of pyroclastic material. So as a general rule, non-explosive eruptions are kind of basaltic to andesitic magma, which have low viscosity and low gas content. And if viscosity is low, non-violent eruptions usually begin with fire fountains due to release of dissolved gases. Lava flows are produced on the surface of the earth, and these will run like liquids downslope along the lowest areas they can find. If the magma emerges along a fracture, such as in Hawaii, it'll result in a fissure eruption. These are often called the curtain of fire. Whereas explosive eruptions are typical of andesitic to rhyolitic magma, which have high viscosity and high gas content. The gases will expand in an explosive fashion and eject pyroclastic material. So pyroclastic material is produced by these violent explosions of gas-laden viscous magma, and debris will form that flies into the air from the lava, and it freezes. And this pyroclastic material will also include solid pieces of pre-existing rocks that were there once part of the pre-existing volcanic edifice that got blasted apart from the volcanic vent. So they're very different type of eruption. Not only did the different types of magma produce different volcanic eruptions, but they also create different volcanic edifices. Low viscosity basaltic magma, for example, creates shield volcanoes, which are broad, gentle domes, and they're called shield volcanoes because their shape represents a soldier's shield lying on the ground. And they form as the product of multiple eruptions of this low viscosity magma that flows so easily that it does not build up around the vent to form a steep-sided mountain. High viscosity magma, on the other hand, tends to create stratovolcanoes, and these are very large, cone-shaped, steep-sided slopes, and they consist of interwoven layers of lava, tephra, and volcaniclastic debris. And these are the stratovolcanoes are kind of the iconic volcanic shape that you associated with Mount Fuji and most of the Cascade volcanoes. Now that we've talked about some of the features that determine how a volcano erupts, let's go back to the question we had at the beginning of this video, which is what type of volcanic eruption created the edifice that we now see at Sibley Volcanic Preserve? There are some features in the park that can help answer that question. First off, it's a very small area, so it probably was not a large stratovolcano that erupted there. Second, the type of rock that is found within the park is basalt, which is, as you remember, is a low silica rock, and the magma that formed it was low viscosity, which further suggests that the volcanic eruption there was not very explosive. And there was not a lot of pyroclastic material and ash throughout the Bay Area from that eruption that has that same age, about 10 to 9 million years ago. So all of those clues suggest that it was not a very explosive eruption that occurred.